Hello everyone. Today Eric will give a talk about building AI agents that reason and act like humans. Eric is an assistant professor at UCSB, and Eric has served as a senior area chair for conferences such as SAO, NASL, EMIP, ACNIR, and NEUROPS, and organized workshops and tutorials at those venues. He has received several awards and recognitions for his work, including Best Paper Award from CVPR and SAR Workshop, Google Research Faculty Award, and Amazon Alexa and Praise Awards, and Cisco Research Awards, and eBay Research Awards, and various gift awards from Adobe, Snap, Microsoft, and so on. Okay, thanks, Eric's talk. So let's welcome Eric talk. All right,
Thank you
Eric,
so
you
much
can
for the
start.
nice introduction.
Okay, great.
Hello.
Yeah, okay, how are you? Yeah,
Thanks so much for the introduction. I'm so glad to be here today to talk about our research on building AI agents that reason and act like humans. All right. So 1,500 hours. People spend 1,500 hours every year just clicking around on the computer. That's roughly 3 months of your life, right? We have gradually become operators of machines rather than creators and thinkers. And today's computers were designed long before AI was even a thing, right? And it's time for that to change. So what if, computers could just act on our behalf, navigating apps, filling forms, and even troubleshooting some errors, so we as a human could really focus on more meaningful creative work. And we believe it starts by giving computers something they never had before, a brain. Right? So at Simular, right, the startup company uh, we are working on, we would like to build general purpose agent that can use your computers just like human, clicking, typing, automating anything from a single prompt. And we call it computer use agent. It has lots of potentials and can work across various industries, including healthcare, real estate, recruiting, insurance, finance, travel, shopping, among others. Right? And basically, we can show an example here. The task is using CRM, find email leads, and grab contacts to draft code emails to them, right? Basically the agent receive this language query, interact with your computer via the most intuitive way, mouse and keyboard control. At every time step, okay, let me play this. Yeah, at every time step, it will take the screenshot as the input and then output the mouse and keyboard control actions. And it clicks buttons, copy emails, moves through pages, filling out the information, and eventually sends out code emails on your behalf. So behind the scenes, it's a computer use agentic framework that it's built on top of all major foundation models, AJS, the one that basically tops the benchmarks on browsers, desktops, and smartphones, consistently outperforming OpenAI and Anthropic on those popular computer use benchmarks. And here is the roadmap to human level computer use. Right, so far we have released 3 iterations of AGS. Exactly a year ago, we released AGS, the very first open source agentic framework for computer use, right? Before, OpenAI and Anthropic released anything in this space. And it was more about memory and learning experience from experience. And at that time, we achieved 20%, which was already the SOTA performance. But there, as you can see, there is still a big gap from the human level performance. But over the years, or within the last year, we have made significant advances, right? In April of this year, we released Agent S2, mainly solving the grounding issue. And today, just weeks ago, right, we released Agent S3, which achieves 69.9% success rate on the golden standard benchmark OS world, basically approaching the human level performance. All right, I'm going to talk about the techniques behind those big leaps. First, ADS. All right, so we should talk about the challenges, right? Why there are lots of challenges involved in computer use, we condense those down to three key challenges. First, the lack of specialized and up-to-date domain knowledge. Agents that use large language models for reasoning can quickly become outdated based on the pre-training data used by those models, right? All the models have some certain cutoff dates. And besides, the various types of interactions and options may or may not be a part of this pre-training process. Second, continual learning to adapt to new answer interfaces. As an agent progresses in a computer use task, it can go through a variety of screens and windows with different interactions and knobs. So agents really need to adapt to those novelties on the fly. And lastly, most user queries or most requests are long horizon tasks, which requires several objectives to be met before a task can be even considered complete. For example, the task help me export charts, graph, or other images from docs files received in an email in notes folder and upload those PNG files to a certain folder in Google Drive for later use, right? And use numbers to name them. So to complete such a task, the agent must complete various subtasks across different applications, say in in Excel, Google Drive folder, uh, right? So and make matters even worse, those large language model agents are highly susceptible to environmental distractions, especially in graphical user interfaces. Like there could be a pop-up window at any time. All right. So to solve those challenges, we go back to the basics, right? What is something we can learn from the way humans interact with and adapt to graphical user interfaces, right? Of course, those user interfaces are designed for humans as end users, while agents represent a completely new class of users. But there are still some key observations that we can learn and utilize for developing better agents. First, we learn from past experience. A lot of tasks, especially on the same app or domain, often involves very similar workflow. For example, the task clear my history in Chrome and clear all cookies in Chrome basically share, this very similar workflow all the way up to the very last step. So if we know how to do the first task, clear my history, then we will try to navigate to a similar web page in order to clear the cookies. And if a task is almost entirely new to us, then the go-to option is to search online, right? This usually provides a lot of solutions and options to choose from, as there are lots of expert knowledge already collected online. And if we are completely clueless about an application, say, maybe you work at a company, you are dealing with, your internal tools only accessible within the company, then there is no way, those large language models can be trained on those interfaces, right? Then yeah, we can explore around, right? Just look out and interact with different options till we find what we are looking for. And then when we are faced with a new task on a similar user interface, then we can recollect the previous exploration experience. All right, so the key idea is to learn from experience. We can learn from previous experience of solving similar tasks, either at the full task level or at the subtask level. And we could learn from expert experience generated by others online. And we can do continual learning, save new experience gained from exploration for the future. So based on those key ideas, we introduce AGS and experience-augmented hierarchical planning. Right? So first, it does hierarchical planning, which means that, it can decompose a full task into a sequence of subtasks and then have a low-level worker to execute each subtasks sequentially one by one. And then how does ADS learn from experience, right? When, it mainly has two modules, a manager agent and a worker agent. The manager agent does planning, which is to decompose the full task into subtasks. And then the worker agent actually interact with the computer interface and complete each subtask. So when generating the plan, the manager will search online to find some relevant expert experience, and meanwhile, it will retrieve some similar task experience from its narrative memory, and then it can fuse the knowledge from both the memory and the web search and augment this knowledge for for task planning, right? And then the worker receives a subtask and then retrieve a closely related subtask experience from its episodic memory. Right? Note that those two memories are sort of different. The narrative memory stores high-level abstractive full task experience, and the episodic memory stores detailed step-by-step subtask experience. And finally, as the agent progresses, it continually summarizes each new task, each full task and subtask experience, and store them back into the memory in a continual learning manner. All right, so the experience certainly play a key role, but it is necessary to have experience in the memory in the first place, right? There is a code start issue, and to address this, we perform an initial self-supervised exploration on some dummy tasks that have no ground truth labels. Basically, we use a task generator to propose a list of popular tasks within a certain domain, and they have agent S to execute those tasks, and finally use a self-evaluator to save the successful experience into our memory. And after deployment, we then can let the agent S to execute any given task, and then it can retrieve some relevant experience from its memory. So yeah, AJS achieved the state of the art on the OS World benchmark a year ago, right? Across different domains. And yeah, we made some progress, but as you can see, there was still a long way to go to close the human agent gap. So what's still missing, right? First, many systems still struggle with pixel precise grounding, which is the ability to localize and interact with exact elements on the screen, like cells in a table, sliders, or specific words in paragraphs, and all the buttons. And this limits fine-grained manipulation and control on those user interfaces. Right? And second, there is an over-reliance on generalist models, right? Those, those models like those advanced generalist models such as Cloud, GPT, uh, Gemini, they try to handle everything from planning to action to grounding, which often results in brittle and superficial behaviors. And this hints at a systematic flow. We are basically pushing those kind of monolithic models to do too much without the necessary specialization. So, and from our preliminary experiments, we noticed that, a strong generalist large language model could be a very weak grounding model, right? So we compare a specialized grounding model like UiTask with the best large language model, generalist large language model at that time. And you can see, this the much smaller grounding model actually performs much better than the bigger generalist model. So then basically we notice that, monolithic system that relies on a single model to deal with everything is actually suboptimal. Then can we combine the best of generalist and specialist to improve grounding and adaptation to the evolving environment? And yeah, it is, right? And it is actually better to distribute the cognitive load to specialists and let the generalist model operate in a purely semantic reasoning space. So then we introduce Agent S2, a compositional generalist specialist framework. Right? For Agent S2, we still keep the manager worker architecture, and the manager and the worker are empowered by the generalist large language model for semantic reasoning. In addition, we introduce mixture of grounding, which consists of different specialist grounding experts for precise and flexible grounding. So we still have the manager to generate the plan and the worker to execute each plan. See, GT is the sub-goal, subtask at this time. Then the worker still execute multiple steps to complete the subtask. But at each step here, the worker will serve as a router as well to the water will automatically decide, which grounding expert to use at this point for better grounding. And we have mainly three grounding experts in the bank. Visual grounding expert, which takes a natural language prompt as the input and output a coordinate on the screen. And textual grounding expert, which uses OCR to identify and select spans of text. The visual grounding expert, it is very challenging for the visual grounding expert to precisely select a text span, but it's fairly easy for OCR technique to do that. And we also have a structure grounding expert to deal with tabular structures to extract data, extract and edit data within cells. And those grounding experts deal with different kinds of grounding tasks, which elevated the cognitive load on the generalist models. And here is an example how it works, right? So let's see, the subtask could be selected the last paragraph in the document, right? So first, the worker could decide to use the visual grounding expert to do that. And then it realized, the agent actually selected the second sentence of the last paragraph instead of the whole paragraph, right? Then our this it realized it's doing wrong, then it can route, the task to another grounding expert, the textual grounding expert, to do text span selection. Now, the agent selects the full paragraph as expected, right? And then this subtask is done, so the manager generates a new subtask, and the worker can route to grounding expert to execute that subtask. All right, agent S2 achieved again the new state of the art on computer use benchmarks across OS world for Ubuntu, Windows Agent Arena for Windows environment, and Android world for smart mobile phone use. Right, and also after our release, Gemini 2.5 Pro was released, then we directly plug Gemini 2.5 Pro in to replace the generalist models such as GPT-4, such as GPT-4o and Cloud, and immediately, it achieved new state-of-the-art success rate. So that's that, our agentic framework are actually agnostic to different frontier models, and we can easily plug in a newer model to get a better performance. All right, so then after AGS2, there are some new advances in the grounding models. Like we say we have GPT-5, we have Cloud 4, we also have Gemini 2.5 Pro with the thinking mode, which has better reasoning capabilities. Then Then after plugging them in, we achieve high performance, but then there is still a major bottleneck, high variance and inconsistency. That said, the same agent might nail a task once and then completely blow it the next time. But the good thing is, while suboptimal individually, different agent runs often succeed on complementary subsets of the tasks. So let's say even we run the same agent multiple times on the same tasks, their performance could vary a lot, right? So inconsistency and high variance is certainly an issue. But what if we we can, combine their disjoint success on those tasks? Then we could achieve much better performance, right? Then a naive idea is to do wide scaling of computer use agents. So instead of simply accept, instead of simply accepting, a single rollout from one agent, we could scale the number of agents to generate multiple rollouts in parallel and select the best. But there are some challenges to even implement that. First, those long horizon trajectories are very informational dense, most of which are actually irrelevant to task success. So they contain lots of information. However, most of those information are irrelevant, are only the key information to the task is very sparse. So then that makes those trajectories very difficult to represent, interpret, and compare, right? So then it requires a more compact and effective trajectory representation. And Moreover, the evaluation itself is very non-trivial. Many computer use tasks admit multiple valid solutions. There is no single right answer. And all the existing automatic evaluation struggles to decide whether a trajectory is correct or not. So for the benchmarks, we are still utilizing some human-defined rubrics or programs to evaluate the success. But even for those human created rubrics and programs, they cannot evaluate multiple valid answers. And therefore, effective wide scaling of computer user agent requires new methods that can do at least two things. First, compactly encode long trajectories while preserving the task-relevant semantics. And second, reliably evaluate diverse solution paths to identify successful rollouts. Then we introduce a new method called behavior based on N to address those issues, right? Our approach starts by generating the facts, or basically, in other words, we try our best to encode the long trajectories into some compact compact representations consists of all the facts relevant to the task. And so by generating those facts, we convert those noisy runs into concise statements about what actually happened at each step, focusing only on the information that directly matters for task success. So basically, we use models, large language models, to describe the differences between screenshots, right? And we also the model could also do zoom in, go to look at the details, right? And and then we concatenate those facts at the individual steps to produce a behavior narrative, which is a clear summary of what an agent did at each step, making those agent runs more interpretable and easier to compare. And with those behavior narratives, in place, we then apply the judge selection to determine which rollout best completes the task. And instead of comparing the raw outputs, the judge grounds its decision in the facts within each behavior narrative, right? We also ask the judge to cite those facts across rollouts. So the judge can, reason comparatively about which attempt is more effective and ultimately selects the best ones. And also with these more compact representations of the trajectories, we can easily feed multiple trajectories, like 10 or 20 trajectories all at once into one region model to do the comparative selection. And previously, we with the raw screenshots, that we can barely even fit one trajectory into a model because of the context window issue. So building on top of the improved baseline, our core contribution, behavior based of N, achieved 69.9% success rate. Uh, this demonstrates us about 7% absolute improvement over Agent S3 uh, on a single run, right? And and about 10% absolute improvement with GPT-5 mini. Yeah, given that human performance is about 72%, those results highlight that behavior-based ON not only surpasses the existing methods by a large margin, but also approaches near human level capability. And yeah, we also did quite some ablation studies. So here I would like to show just a few. Uh, we show that, the agent's performance can actually increase with increased number of rollups. So it scales well, right? We can see the performance gradually improves as the number of rollups increases. And we also took a look at the tasks where our judge could improve performance. Uh, so we also did a human alignment for evaluating those tasks. So first, on the tasks that our method could potentially improve upon, basically not all failures, not all success. The judge was actually correct for 92% of all the tasks. And on the full test set, the human evaluation is actually 76%. So that's the OS world eval itself is suboptimal. As we said earlier, right? Those human curated programs cannot validate different answers. Right? They only allows one single correct answer. But typically there are multiple ways to complete the same task. So our agent actually achieves, 76% success rate according to human evaluation, which demonstrate a huge potential for using our judge to evaluate those computer use agents and the tasks. All right, so at Simular, our company building computer use agents, we are not just testing our algorithms within the sandbox, right? We are actually building real-world products beyond the benchmarks and and people so that people could use every day, right? So we have Simular Pro for enterprise use. We have Simular Browser for general exploration and the cloud solution as well if you don't want to do it locally. And we also have customized service for large businesses. All right, so then we almost achieve human level performance, but with behavior-based run, right? But the single run is still not there yet. If we want to improve the performance of single run, then we still need to improve the reasoning capabilities of those models, other large language models behind the doors, or those open source ones that could be deployed locally, right? And that requires the models to actually reason like human, or even better than human. So next, I would like to briefly talk about our recent works on improving the reasoning capabilities of those large language models. So I guess everybody is aware of chain of thought reasoning, right? So DeepSeek R1 is doing chain of thought reasoning explicitly. Basically, they are using RL to reinforce the model to generate a chain of thought reasoning path before generating the final answer. But here is the problem. Humans don't actually think that way, right? At least not all the time, right? Chain of thought is inherently sequential and discrete. Each token builds, on the last one in a linear path, right? So do we actually think like that? Do we, always verbalize our thoughts word by word before generating the final answer? Of course not. Humans, by contrast, think more fluidly, right? We reason with continuous abstract concept. We could hold multiple ideas in mind, and we often jump between high level goals and fine details from times to times. So therefore, we introduce soft thinking, which is a training-free method that mimics a human-like soft reasoning by generating continuous abstract soft tokens. And those soft concept tokens could smoothly blend multiple meanings of those hard tokens at the same time to enable continuous representations and seamless exploration of diverse reasoning paths. All right, here is how we do it. Right, this is the reasoning process of soft thinking. So first, the input context is still considered uh, 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 as the normal input as usual, right? So we are still taking the discrete tokens of all the input contexts as the input to the model. But at each thinking step, basically after the think token, we generate a soft concept token, which basically keeps the full probability distribution. We do that by creating the new input embedding with a weighted mixture of all the token embeddings. And then we feed this soft token back into the model and repeat step 2 and 3 all the way until the end of the thinking token, right? So, and after the thinking process is done, we generate the final output with discrete tokens again. So basically during the thinking process, we have a soft token that preserve all the potential information of multiple hard tokens. So and this can preserve a superposition of the reasoning paths, which avoids some premature collapse and allows richer, more flexible thought. And then we also feed this soft token back as the input to the model to continuously generate the soft reasoning path, right? And then after the thinking process is done, we verbalize the final answer with with discrete tokens, the hard tokens. And here is a visualization of the soft thinking process. Right, so the model can actually represent some nuanced in between concepts that are not captured by any single word. Right, here you can see at many steps it captures the meanings of different words, and but it is still readable and interpretable. We can always visualize the thinking process with the most probable words in the sequence. Here is a comparison between standard chain of thoughts and soft thinking on a multiplication problem. So basically, for soft thinking, we select the token with highest probability at each step for readability and interpretability, right? Those red tags denote some repetitive useless words. And as you can see, soft thinking use much less tokens to arrive at the final correct answer, while in this case, the chain of thoughts thinking generates quite some repetitive useless words that could be removed. All right, so the soft thinking method improved accuracy on multiple math and coding benchmarks by up to 2.5% and reduce the token usage by up to 20%. Right. So basically, soft thinking makes the reasoning models both smarter and more efficient. All right, so yeah, soft thinking is it's about, improving the reasoning process of those large language models. And there are also some recent work that try to deploy the reasoning models for solving multimodal reasoning tasks. However, we noticed that, you know, more thinking does not necessarily lead to better performance. And in contrast, the more the reasoning models think or gen the more visual hallucination it could have. So here is so for in this figure, Quen 2.5, 3B, and Quen 2.5, 7B are the base models, and all the other models are using the Quen models as the base model, and and and, and use IR to to fine-tune the model for multimodal reasoning tasks, right? And as you can see, although their reasoning accuracy are getting better, the perception accuracy are actually worse. So that said, longer thinking actually leads to more visual hallucination. And we can look at an example here. So there is a perception task. Is there a sports ball in the image, right? The base model, Quen 2.5 VL, could actually answer this question correctly. No, there is no visible sports ball in the image. The image shows a baseball game with a batter, catcher, and umpire, but the baseball itself is not visible, which is right? There is no baseball in the image, as we can see. However, the R11 vision model, which is supposed to be, a better reasoning model for those kind of tasks, generates a interesting answer. Let me start by analyzing the image itself. Although no specific mention of a sports ball is made, the context strongly implies its presence, as baseball games inherently involves a ball. So yes, there is a sports ball in the image. So as you can see, the reasoning model heavily rely on its pre-trained knowledge to answer this question, right? Which is a obvious hallucination. So instead, the model, should look into the details of the image more. So basically, when the model try to utilize its pre-trained knowledge to do the reasoning without even grounding back to the original input, then it deviates from the input, right? And generates hallucinations. So in this work, we analyze this behavior, identify the problem, and introduce a new benchmark and some potential fix in the paper. So I'm gonna skip the details here, but welcome to read the paper. And those reasoning papers have been accepted to new RIPS this year. And
Hi, Yuriko. I just remember
yeah, and
uh,
one potential
hello.
solution to address those hallucinations in multimodal reasoning tasks is to let those models ground back to the image, right? Then, so
Hello, Yuriko.
we
Sorry.
have another concurrent work
Can you hear
called
me?
GREAT, teaching multimodal large language models to think with images. Know that, this work was actually done before OpenAI released their thinking with image feature. So in this work, in addition to letting the model, the reasoning model, to generate the reasoning path word by word, right? We also ask it to generate visual anchors, the the bounding boxes of a certain region in the image, which serves as the visual anchor to ground back to the original input, right? And it this method reinforces grounded reasoning by eliciting those models' native grounding capabilities with just 20 examples. So it's very sample efficient. We can just use 20 examples to elicit those models' native grounding capability during the reasoning process. So the reason why we can do that is because those models already have the grounding capabilities. They just don't know how to use them in the reasoning process, right? Then we can use R to elicit their behavior, then achieve much better performance. And all right, so we are almost time. And so what's next, right? So yeah, so we have demonstrated some advances in improving the reasoning capabilities of those models. Then the next step would be apply those reasoning capabilities for long horizon agentic tasks. Right? And also, so far, the SOTA models are still built by humans, right? I guess the human knowledge, the inductive bias still play a very big role there. Can we build agent that can evolve by itself um, from learning from by learning from experience and evolve by itself? And then yeah, and we already achieved near human performance. Can we further scale computer use agent for superhuman performance? They are supposed to work better than us. Yeah, and eventually they will work better than us on those tasks. Uh, But so and also, currently we are still relying on those large foundation models for the best performance, and there is a clear gap between open source models and those closed source models. So we need to close that gap and also develop much smaller computer use agent to deploy on our devices. All right, thank you so much. Here is the reference of all the papers I talked about today, and I'm happy to answer some questions.
Hello, thanks for Eric's great talk. So any question from the audience?
Oh, hello? Yeah,
Can you hear
sorry,
me? Can
I'm
you hear me?
muting anyway, I didn't hear you. Can you repeat?
Can you hear me now?
Yeah.
Okay, great. Thanks for your great talk. So currently, any question from our audience? So if you have any questions, feel free to ask. Actually, I have several questions. So for
Mhm.
the non-horizon reasoning, I think is really important. And so regarding this issue, do you think we need to design new architecture for this, or do you think a transformer or like Mamba can do this, or we don't need to design new network architectures for this, or just design new methods, some optimizing methods?
Okay, so yeah, that's a very interesting question. First, I believe even with the current models, right, even with the default transformer architectures, there we are still not training them enough in terms of reasoning, right?
Mm.
So, I guess from the method perspective, we can still design better reinforcement learning methods to train those models over multiple turns, right? So currently, I think when we talk about R1 or some similar mo reading models, the, they are still very good at single turn reasoning. So that they generate the reasoning path before finalizing the answer, right? And there are some recent attempts to make it multi-turn, right? And but I don't think it it has been there yet. So there is still a large space for improvement. And in terms of model architecture, yeah, there is a hierarchical reasoning models and some other parallel works like Mamba for more efficient. Yeah, it's very interesting. So typically the Mamba architecture should be more efficient for long horizon tasks, right? Um, but does this efficiency, is there any trade-off between the efficiency and the capabilities? So that I'm not very sure. So I'm not an expert on Mamba, right? So, but I would love to see some parallel or efforts on this.
Okay, okay, great, great. That answer my question perfectly. I have another question about your interesting work about the soft thinking. So I would like to know how to adjust the weights. In your slides you showed that there are some weights that we need to adjust. How you in the soft thinking process, how we adjust the token weights and also and how to design to choose each thinking style for each task. Yeah, like this. The step three, and follow this. On different tasks, how can we choose different thinking style? No, should we choose soft thinking style or we choose hard thinking style and so also some other reasoning process. How we choose that for different tasks.
Oh yeah, the soft thinking method is very simple. But basically, at each thinking step,
Mm,
we have a mixture of embedding as the
mm,
soft token. So
mm,
the soft token is essentially a weighted sum of all the token embeddings.
okay.
And then we feed this back to the model to generate the next token. So because it is like an interpretation in the embedding space, right? Because we are doing weighted sum there. So that's why, we don't even need to train the model to accept those new tokens as their interpretation of the original embedding space. Essentially there is no outer distribution issue. That's why the method can be training free. But to make but there might be some diversity issue if we always take the weighted sum of all the token embeddings with their probabilities, then you could leverage some different sampling strategies there. Let's say you sample the top K tokens to form the weighted sum, uh, top five, or basically some different sampling strategy. And there is a follow-up work already on analyzing different sampling strategies on the soft thinking algorithm, which is quite interesting. Um,
Right.
and of course, there are some other details that I didn't get the time to talk about. Like we
Mm,
also introduced the cold stop to do early stopping based on the entropy of those uh, token embeddings. But yeah.
great, great. Oh, so can you show just our examples of what is a concept token? So the definition about the concept token, because I think this is a new term in this era, concept token.
Uh, okay, so let's see. You can see here.
Yes, I can
Let's
see that.
see. We see. the model will always generate a probability distribution over the vocabulary, right? See, there
Mm,
are four tokens here with different probabilities.
mm,
The concept token is simply a weighted sum of those four tokens,
mm. Okay.
right? So it is a weighted sum of those four tokens whose weights are their probabilities.
Okay. Okay. Great. Great. Okay. So, yeah. Thanks for your answer. We have another question from the audience. You
Mhm.
can also say the chat. Uh, do you share paths for agent to not just recall past experience, but to actually learn from them and get better at reasoning with each task?
Do you see a path for agent to not just copy, but to actually learn from them and get better at reasoning within each task? Mm, Okay, to not just recall what. Okay, so I just want to understand this question. Did you mean that, the agent can retrieve a past experience and get better on the same task? Or
Yeah,
the
thank you for the presentation. It is really nice. I don't know if I understand correctly, but what I understand from Agent S that is somehow rely on store experience for adaptation. And I was wondering if it is use this experience to take or to abstract some knowledge from it and to make it better reasoning for the each other task, not just retrieve them or take them as they are previous experience.
Oh yeah, so those experience are basically abstract summaries of previous tasks.
Oh, okay.
But
Yeah.
it's not a not a step-by-step demonstration. So especially
Mm.
for the full task experience, it is it is summarized knowledge of a similar task. And this knowledge might be transferable to some similar task. Then
Oh,
if that's the case, then they are useful, right?
oh, yeah, yeah. Yeah, thank you so much.
Mm.
Okay, great, great. Yeah, thanks for Eric's great talk, and also for your time. And so let's end this today's seminar, and we will have another seminar next week, Friday at the same time. Okay. Uh, so hi, Eureka. Thank you.
Thank you so much.
So, see
Thanks,
you.
Eric. Great
Mm,
talk.
Great
Great
talk.
having
Bye.